Now, the symbol that we will use for so let me back up for a second. Typically, wires themselves have a very, very low resistance. They don't have much resistance at all. So, when we need to have some resistance in our circuit, there is a particular circuit element that we will put into the circuit for the sole purpose of increasing the resistance of the circuit. That object is called a resistor. The symbol that we will use for a resistor is a sharp sawtooth little thing like that. Now, when drawing it, be careful, make sure you make it a sharp tooth thing, because if you get kind of sloppy and kind of, do something like that, a little spring-shaped thing, that actually is the symbol for something else that we'll see later on, an inductor. So make sure that you have a nice sharp-toothed image. So we will basically assume, because the resistances of wires tend to be relatively low, that all the resistance in our circuit is present in the resistor. We'll assume that the wires are essentially resistance-less compared to any other resistances of resistors that we have in the circuit. So let's imagine we've got a situation like this. Let's imagine we've got maybe 6 volts here and a resistor of, let's say, 0.100 ohms, and let's see if we can figure out what the current is. Well, what's the direction of the current going to be? Remember, current will flow from the high side to the low side, so in this case, the current is going to go counterclockwise. So what is it? Well, we know V equals Ri. V equals Ri. That is very important. I equals V over R. So what do we get? V is 6 volts divided by R, 0.100 ohms. So we get 6 divided by 0.1, or 60.0. And what is a volt per ohm? Well, you could go back to the definition of ohms, or remember, if you use the standard SI units, you'll get the standard SI unit for your quantity I, which we know has got to be an amp. So 60 amps. So that's the current in this circuit. Now, this looks like a very, very simple circuit, and it is, but it's actually the circuit that's used for something very, very important, with one little exception. This looks like a connected circuit that basically is going to keep its current going constantly. We could put a little switch in here, which we could draw like that. So that's how we might draw a switch, so that we can have the circuit open so that no current would flow, or closed so that the current does flow. So we could choose, what do we want? Do we want it open or closed? On or off, off, like that. Well, that's exactly the circuit diagram that we would use for something most of you have all probably used before. Here is our circuit diagram, and that is for a flashlight. So a flashlight is basically power source, battery or batteries, connected in line, so positive terminal connected to the negative terminal, which is then connected to the light bulb with a piece of metal going through a switch, so you can connect it or disconnect it, and then back down to the other terminal of the battery. The bulb is actually the resistor in the circuit. So the bulb filament, that's what's actually creating the resistance for the circuit. As the current goes through the bulb, the filament heats up. It gets very, very hot. It gets so hot that it starts to glow. It produces light, and that's what makes the light for the flashlight. But the basic circuit diagram is exactly just what we were talking about here. Here's our battery, our power source, the high side, the current comes around, the filament is the resistor, and then some switch that we could use to turn it on or off. Okay, now, how much power is used by a circuit? Well, let's remember, when a charge goes from some point to another point, so we've got some charge and we move the charge from one point to another point, the voltage difference is equal to the change in the potential energy per charge. So that's the voltage difference. In other words, the change in the potential energy is equal to the voltage times the charge. So we move some charge through some potential difference, So maybe we could write this as delta V, delta PE, delta V. We move our charge through some voltage difference, delta V. The change in the potential energy is delta V times Q. Well, how much power is used? Remember, the power is energy per time. So that would be delta PE per time interval, delta T. So we'll divide this by delta T. And what do we have? Well, we have delta V times Q over delta T. What's Q over delta T? That's the charge per time. So if we move a bunch of charge, we could call this, say, delta Q over delta T. Well, the amount of charge per time, that's the current. So the power used is basically the current times the voltage difference. So we basically have that the power is equal to the current times the voltage through which the current is moving in our circuit. This is a very, very general result that can be used for any kind of circuit. For a resistor in particular, we know that V equals Ri. So I equals V over R. So we could write this also as V over R times V, or V squared over R. We could also write this with V equal to Ri, so I times Ri, we could also write this as Ri squared, or I squared R. So the power used in a circuit is I times V, but if it's a resistor circuit in particular, we could write it as V squared over R, or Ri squared, and either of those ways also. So let's stick some numbers in. Back with our circuit before, when we had 6-volt battery and a 0.100 ohm resistor, how much power do we get? Well, we've got the voltage, we've got the resistance. We could use this one, V squared over R. This will be 6 volts over 0.100 ohms squared, or, 6 volts squared divided by 0.100 ohms. That would be 36 divided by 0.1, 360, 360. What is a volt squared per ohm? Well, you could go back to your definition of those quantities, or just remember, those are the standard SI units. What's the standard SI unit for power? A watt. So 360 watts. There we go. Now, where is that energy going? How are we losing that energy? Well, where in this circuit is it going? It's being lost by the resistor. Think about the light bulb filament. What happens to that light bulb filament? It heats up, and it's losing energy because it's heating up. It's giving off heat. It's also giving off light. Well, these resistors in a circuit will heat up and will lose energy because of that heating. Sometimes this is referred to as joule heating. Joule as in the joule of energy. And that's how much power will be lost because of the resistor heating up. Okay. Now, we talked about the resistance of resistors, and we talked about how we kind of assumed that the resistance of a resistor was a constant quantity. But if we think about current flowing through a resistor, imagine we've got some object and there's current flowing through here. Well, as the current flows through, we know this thing is going to heat up. The temperature is going to increase. Joule heating is going to create heat, and this thing is going to heat up. So typically the resistor, the temperature is going to go up. Now, what happens when that occurs? Well, if we think about it, what's going to happen as these charges try to move through this object as the object gets hotter? Well, think about trying to a group of people trying to run down a hallway. Imagine that the hallway has got lots of people in it, and all the people in the hallway are standing very, very still. And then imagine this group of people tries to run down the hallway. They have to go around all the people that are standing in the hallway. But now imagine that the people in the hallway are not standing still. They start flailing around like this. Now, is it going to be easier or harder for the people to run down the hallway through these flailing arms and legs? Obviously, it's going to be harder for them to run down the hallway. Well, that's kind of like what's going on here. When we have a very cold resistor, the atoms and molecules that make up the resistor are not moving around very much, and it's much easier for the charges to move through them. However, as the resistor heats up, the atoms and molecules that make up the resistor start moving around a lot more, and it makes it more difficult for the charges to move through it. Well, if it's harder for the charges to move through it, it means the resistance increases. So, if we actually look at the resistance of a resistor, or the resistance of an object, as a function of the temperature, it turns out that the resistance increases with temperature for many materials. Well, if we can actually imagine going the other way, what happens if we decrease the temperature? For some materials, this line will actually come down and cross the axis. It actually hits the axis at some non-zero temperature. Now, what does that mean? Well, it means at that temperature, what's the resistance? Well, the resistance is zero. We call this kind of material a superconductor. And the temperature where this occurs, we call this the critical temperature. The superconducting critical temperature. There is a very, very big area of research in material science trying to determine materials with larger and larger critical temperatures. Now, what does that mean? Well, to find materials that become superconductors not at very, very cold temperatures, but at higher temperatures. For example, there are certain ceramic materials that have been discovered that become superconductors at around the temperature of liquid nitrogen. Liquid nitrogen is fairly easy to make, and so you can make these materials become superconductors fairly easily. However, if you just have liquid nitrogen sitting out on your bench, eventually it will turn into a gas, and it won't be able to cool things down anymore. However, if you could get a material that had a critical temperature that was so high that it was, say, on the order of 20 degrees centigrade, well, what's that? That's room temperature. You'd have a material that was a superconductor at room temperature. And you'd be able to do all sorts of things without even having to cool it down at all. So there's a big, big area of research trying to determine materials with higher and higher critical temperatures, with the hope that maybe someday someone will discover something that is superconducting at room temperature. So how can we figure out what the resistance of a particular resistor is, just say from its shape and material? Well, let's imagine we have a very simplistic shape for a resistor. Let's imagine it's just a perfect cylinder. Let's imagine it has some length L and some cross-sectional area A. Well, what sorts of things do we think might affect the resistance? Well, what about L? Now, would a longer resistor have a higher resistance or a lower resistance? What do you think? Well, imagine you're trying to run down a hallway, and you've got a hallway that's twice as long. Is that going to be easier or harder for you to run down? Well, obviously, twice as long, it's going to be twice as hard. So the longer the hallway, the more difficult it is to get down. So the bigger L, the larger the resistance. That makes sense. So we'll say R is proportional to the length. Now, what about the cross-sectional area? If we increase the area of the resistor, will that make it easier or harder? Well, imagine, again, rather than one person going down the hallway, imagine you've got a crowd of people trying to run down a hallway. If you have a larger hallway, would that make it easier for the crowd to run down or harder? Well, a larger hallway will make it easier for the crowd to run down the hallway, right? They'd be able to spread out more, and it would be easier for them to run down. It would be less crowded. So the larger A, the less the resistance. So the resistance is actually inversely proportional to the cross-sectional area. All right, well, What about the material? Obviously, different materials have different conducting properties. We talked about that before, remember? Conductors and insulators. So somehow the material is going to affect the resistance. Well, we'll put this all into one equation and write this as R is equal to L over A. And the material we will put in terms of a quantity that we will call rho. This is a lowercase Greek letter rho. And it is what we will call the resistivity. The resistivity of the material. So, the resistivity only depends on what the material is, not what the shape or size of the resistor is. Just what is the material that we're using to make our resistor. The units of resistivity we can find by inverting this. It will be the units of R times the units of A divided by the units of L. Which will be what? Well, what are the units of R? Units of resistance, ohms. What are the units of A? Cross-sectional area, that'll be meters squared. And the units of L, length, that'll be meters. One of those cancel, and we find that the units of resistivity are ohm meters. Okay? There we go. Let's stick some numbers in here.